The new section is entitled Counting. I think all students or all people should know how to count. Let's get down some notation first. Talk about factorial. N factorial. N will be some number, factorial, like 3 factorial, 4 factorial, 11 factorial. This is read as N factorial. And what N factorial is, normally is written from high to low, but it's 1 times 2 times 3, all the way up to the number before N times N itself. It's from this, the product of that number, all the way down to 1. N times the number before it, times the number before it, times the number before it, all the way down to 3 times 2 times 1. That is 5 factorial. Start at that number. 5 times 4 times 3 times 2 times 1. That's 20. And then multiply that out to 6. 5 times 6, 20 times 6 is 120. You'll have a factorial button in your calculator. Learn how to use it. By definition, 0 factorial is 1. This is where n is bigger than or equal to 0. It's at least 0. 0 is at least 1. The 0 factorial is defined to be 1. 1 factorial is 1. 2 factorial is 2 times 1, or 2. 3 factorial is 3 times 2 times 1, or 6. Now here are 2 important facts in counting. Start off with their number of ways to arrange, think in a line, to arrange n objects is n factorial ways. Number of ways to arrange n objects is n factorial. N factorial. In other words, if the objects were A, B, and C, maybe they're books, okay? They're books, and the names are A, B, and C. Why call them by their real names, which has 5, 6 words in them? Just call it textbooks or the books A, B, and C. In your bookcase, how many ways can you arrange them? Well, the number, reading the top 2 lines, the number of ways to arrange 3 objects is 3 factorial, which is 6. 3 times 2 times 1 is 6. There should be 6 different ways of arranging these 3 books. And let's show that. You can have A first, and then B, and then C. Or with A first, it can then be CB. With B first, you have AC, or you have CA with B first. With C first, you can have A second and then B, or B second and then A. These are the 6 different ways of arranging these n objects. There are n factorial ways of arranging n objects. N is just a placeholder for a number. I need to tell you what n is. There are 3 objects, so you should say, oh, 3 factorial. If I tell you there's 11 objects, you should say, oh, they can be arranged in 11 factorial different ways. Whatever n is, say factorial, and that's the number of ways of arranging it. 9 objects, how many ways can you arrange them? 9 different ways. They all have to be different. Suppose there are n objects, and you want to pick r of them. The order doesn't matter. 10 people come to you looking for a job. The people are the objects. So in that case, 10. 10 people come to you looking for a job. You want to pick 4 of them. You want to pick 4 of them. But the order doesn't matter. In other words, if suppose there are 10 people numbered 1 through 10. If the boss picks these 4 people to be hired, is this the same? So first he picked 3, and then he picked 4, and then the boss picked 7, or maybe it's a she, then she picked 6. Or maybe this person first picked 7, and then 4, and then 6. Oops, I want these. Yeah, and then 6, and then 3. But these are the same 4 people in this first case. These 2 cases have the same 2 people. They both have 3, they both have 4, they both have 7, and they both have 6. They're the same 2 sets of people. Now, in terms of if you're hiring 4 people for the same job, these 2 lists have to be said to be the same. It's not really different. Now, if you said the first person I'm going to hire will be the president of the company, and the second person, the vice president, and then the treasurer, and then something else, that'd be different. Because in the first case, 3 was hired to be the president. In the second case, person 7 was. Vice president is still 4. But in the top one, the treasurer is person 7, while in the bottom, the treasurer is person 6. It's different when the order matters. And what we're doing on the top, the order does not matter. The order does not matter. Okay, you want to pick r of them. There are 10 objects, all the same. And you want to pick r of them. How many ways can this be done? How many ways can this be done? And the answer is it's NPR. That's the notation. The left number, n, goes on top factorial, and the difference between the 2, they get factorial in the bottom. So in our case, we have 10 and we want to pick 4. So it's 10 factorial on top and 4 factorial on the bottom. Excuse me, the difference on the bottom. 10 minus 4 is 6. And to show you that this somewhat makes sense, for the first, so this means 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Divided by 6 times 5 times 4 times 3 times 2 times 1. If you want to, you can say, oh, that's 6 factorial. So in front, you have literally what's in front. You have 10 times 9 times 8 times 7 times 6 factorial. Divided by this, which is 6 factorial. So the 6 factorials cancel out, and you're left with 10 times 9 times 8 times 7. And the reason that makes sense to be the answer is because for the first person that you pick, there are 10 people in front of you, and you want to pick 4 of them. 1, 2, 3, 4. You have 10 choices for the first person. But you chose this person. This person is hired, and you are no longer considering whether or not you're going to hire this person anymore. That is, when you go to pick the second person to hire, person 10 is already out of the picture. There's only 9 possible workers left, potential workers. Now you hired 2 of them. You hire person 7 and then person 3. Well, there's 8 people to choose from to hire as a third person. And then the last person comes from a group of 7. But this is exactly what we got down here. That is, this formula works well. This is when you're picking a number of objects from a number of objects, and the order does not matter. Okay, this is important. It should definitely be written somewhere. The order doesn't matter. That's when you use permutations. This is called the formula for permutations. How many ways can you choose R objects from N? Now, in this last case, that was when all the objects were different. Suppose you have a group of books. You have a group of 10 books, but some of them are the same exact book. You have 3 of this type and 2 of another type. So, suppose you have 10 bucks. You have 10 bucks. And the books happen to be called A, B, C, and D. You have 3 A's. You have 2 B's. You have 2 books exactly the same. The title is B. I can say longer titles, or why not just A, B, C, and D? And we have 4 C's and 1 D. Total of 10 books. Now I ask you, how many different ways can you arrange these 10 books? Now, normally, if they were different books, the answer would just be 10 factorial. How many different ways can you arrange n objects in factorial ways? Read the top. The number of ways to arrange in a line n objects is n factorial. The number of ways of arranging, and we actually talked about books. Let's see if it's still there. Books A, B, and C. I wrote down the 6 different ways of putting them in order, putting them in the bookcase. Now, the thing is this time we have 3 books that are the same. In other words, let's just call the A books A1, A2, and A3. 4, 5, 6, etc. 2, 3, 5, 6, 10. Okay. That didn't leave enough space. So you have A1 and a couple of other books, and then A2 and a few other books that used up 7, 8, 9, 10. And you have the other bucks. I don't really care what they're called. Not even, what if they were all different? Let's just assume for a moment they're all different. B, C, D, E, F, G, and I. Now, of course, when you go over to the bookcase, you don't recognize that as A1 and this is A2. You recognize it as A. So in other words, so this is one of the many different ways I could arrange these 10 bucks. However, if you were to switch some of their A's, that is, you put A2 here and A1 here, and you keep A3 here, and everything else is the same. The question is this going to look any different to you? And the answer is no. First book is A, second book is B, and then C, and then A again, and then D, and they're both E's, they're both F's, they're both A, they're both E, to say G, and they're both I books. Well, we can't count these the same. We can't count these the same. In fact, we would be counting them 3 factorial times too many. Anytime you have every time you put the books in the bookcase, there will be 3 A's. And any way you could arrange them, you could arrange them 6 times in that same fashion. In other words, here was the second way of listing the first one. A third way of listing the first one is to put A3 here, and A1 here, and A2 there, and everything else stays the same. There are 3 factorial different ways just arranging the A books that we shouldn't be counting as 3 factorial. We should count this arrangement as 1. That is why I'm dividing by 3 factorial. In any place you see the B's, you can interchange the same 2 B's, and you won't notice a difference. That is, we're counting every arrangement 2 times too many. So let's divide by 2 times. That is, divide by 2 factorial. The C's. Wherever you have the C's, if you permuted those 4 books, which can be done in 4 factorial different ways, if you rearrange, that means permute. If you rearrange those 4 books, you could rearrange them in any given order of the 10 books. If you just switch the order of those 4 books, 4 factorial different ways, you didn't really make a change. You're double dipping. In fact, you're quadruple dipping. You're counting it 4 factorial times. Well, that's not 4 times. That's 24 times. It's much more than quadrupling. 4 factorial looks to be like 24. 12 times 2 is 24. Every arrangement that you can think of, you're going to be counting 24 extra times, or 23 extra times. That is why we divide by it. And then you divide by the 1 factorial, but since that equals 1 anyways, and dividing by 1 there's no need to do, here is your answer. There were 10 books, so if in fact you have n books, so you get n factorial on the top, and then you put down the repeats. You say 1 book came up n1 times, and the second book, another book, came up n2 times, and the third book and the fourth book, etc., all the way up to the kth book came up n sub k times. These are just the number of times one of the book comes up. This is the number of times a different book came up. And this is the number of times yet a different book came up. Come up means we have 3 of the same books. It came up 3 times. So a good standard problem now would be to find the number of ways to arrange the letters in the word Mississippi. Or actually, another good one I learned the other day, I didn't realize it was a good one, is the word mathematics. How many different ways can you arrange the letters in the word mathematics? Well, first thing you have to do is know how many letters there are. That's 5. Another 5 is 10. So there's 11 letters. Factorial. Some of them are n's. 1, 2 n's. So you divide by 2 factorial. The next letter after m is a. There's 2 of those. So you divide by 2 factorials. T, there's 2 of them. So it's 2 factorial. There was 4 of them, it'd be 4 factorial. H only came up once. You don't need to bother to write the 1 down. E came up once. I, C, and S come up once. So here is the answer. This is the number of different 11-letter words you could make using the words, using the letters for mathematics. It is you scramble them up. You scramble up the letters. And you make silly words like maybe T is first, and then M, and then T, and then the letter I, and then the letter E, and then A, and then S, and then A, and then M, and then H, and last C. If I didn't make a silly mistake, if it did, it's no big deal. But there are 11 letters, so it looks promising. This word, or this arrangement, T, M, T, I, E, A, etc. That's one of the ones in here. Now, if you just switch the 2 M's, it shouldn't be counted again. That's why we divided by 2 factorial. Okay, you need to know that. So more formally, the rule would state this. If you have n objects to arrange, and there are n1 of one type, and m sub 2 of a second type, different from the first, etc. And n sub k of type K objects. So let me see what I wrote so I can finish it up nicely. This can be done. This can be done in, well, there are n objects to arrange, so that's n factorial. And they're not all the same. Some are of one type. You divide by n1, n sub 1 factorial, n sub 2 factorial, all the way up to n sub k factorial. If there are 6 different types, then k would be 6. You would have the first type, you would have n2 of the second type, and you would have n sub 6 of the sixth type. There are 6 different types. Types would be like there were 2 m's in the word mathematics. Okay, the next thing we have to talk about, and then we'll do problems related to them, is combinations. Here, the order matters. You have different orders, or should be counted separately. For example, if you have the letters A, B, C, and you want to choose 2 of them. Okay, from A, B, C. Choose 2. How many ways can this be done? But this time I'm telling you, the order matters. Well, you can have A and then B, or you can have A and then C, or you can have B and then A, and then B and then C, or you could have C and then A, or C and then B. There are 6 different ways of choosing 2 of them. Now, if I didn't tell you that the order matters, if I say the order does not matter, well then this would be 3P2. From 3, you want to pick 2. So the left number goes first in the numerator, factorial, and the difference, which is 1, gets factorial in the bottom, and you have 3 factorial divided by 1 factorial, which is 3 times 2. I want to see something really quickly. Okay. Now that's true. Now, when it comes to combinations, it's NCR. N is the number we're starting with. We want to choose R of those objects, and you also have to multiply by N minus R. So in our case, we have 3C2. So you get that number factorial in the top, this number factorial in the bottom, and the difference, which is 1, factorial in the bottom. This is 6, this is 2, 1 factorial is 1. So you have 6 divided by 2, which is 3. And I've been doing something terrible, but we'll clean it up right now. For combination, the order doesn't matter. When it comes to permutation, it does matter. See if I could figure out where that NT is. It absolutely does matter. Okay, so since it doesn't matter, AB and BA should not be counted twice. AC and CA, bye-bye. BC and CB are the same. In fact, there's only 3 combinations. And that is what we got at the end. We got 3. We got 3. Combination, the order does not matter. Combinations, the order does not matter. For permutation, the order does matter. Write it down. For combination, the order matters. Suppose there's a lottery. Suppose there is a lottery. And you want to choose 5 numbers from 1, 2, up to 30. I'm going to choose 5 numbers from the 30. Now, if you think about it, if the 5 numbers are 1, 3, 7, 9, and 13. Well, if your card says 13, 1, 3, 7, 9, if I left one out, I'm sorry, you're a winner. If your card says 3, 7, 1, 13, 9, you're a winner. Well, I don't know much about the lottery. I'm assuming, and if I'm wrong, well, I'm defining the problem. I'm assuming these are the same. I'm assuming the order does not matter. So since the order does not matter, we use the combination 1. From 30, we want to choose 5. And for those of you who use your calculator, you may have a combination button, and you can type in the 30 and the 5, and it'll crank it out for you. But this means the left number factorial on the top, the second number factorial on the bottom, and then the difference, which is 25 factorial on the bottom. Okay, work that out. This is where we're assuming the order didn't matter. But what if the order does matter? The order matters. That is, these 3 tickets, these 3 lottery tickets are different. They're different. They have the same 5 numbers, but they're different because the order is different. That is, if 1, 3, 7, 9, and 13 are the 5 numbers that came up, you may not have won. You have to say get it in that order. That'd be a winner. The others would be a loser. You have to get it in a particular order. Okay, now, if the order matters, that implies permutations. So from the 30, you want to permute 5 of them. And that's going to be the left number factorial on the top and the difference factorial on the bottom. That would be, this here will be the number of different lottery tickets there would be if there are 30 numbers and a ticket only has 5, but the order matters. It will be 30 times 29 times 28 times 27 times 26 times 25 all the way down. But that's going to be killed off by the 25 factorial in the bottom. So it's whatever 30 times 29 times 28 times 27 times 26 is. Personally, I prefer to put 5 slashes. There's 30 numbers I can pick from for the first one, and 29 for the second, and then 28 for the third. A number cannot repeat. So that's if the order matters. I don't think it does. But if it does, fair enough, then it's the one in the bottom. So one thing you should have learned was the answers are completely different if I say the order matters or doesn't matter. Okay. Now, suppose you want to make a license plate. And you want 3 digits followed by 2 letters. Now, let's suppose, for argument's sake, 3-digit plates, there are 10 of them. And just 2-letter plates, there's 8 of them. You have the 10 plates. 1, 2, 3, 4, 5, 6, 7. Like I said, suppose for the 3-letter plates, there were only 7 different combinations, 3 digits. And for 2 letters, well, whatever we fit in, 1, 2, 3, 4, 5. So, under the 7, all the different 3-digit plate numbers you can have. Maybe the first one is 1, 3, 7, and the next one is 2, 11, etc. 3 digits. And for the letters, we have 2 letters. We have R, S. We have K, N. We have Q, V. Well, we can put these plates together. You can always put, remember that says 137. You could put 137 with RS, or 137 with KN, or the second set of numbers. In fact, just with 137, you're going to get 5 different plates. And then with 211, which is the next one, suppose. You can have RS after it, or KN, or QV. You're going to get another 5. And then for the third digit plate, the third 3-digit plate, you're going to get 5 more. And you're going to get 5 more for each of them. In fact, you're going to be adding 5 to itself 7 times, which will be 5 times 7. If they really were just 7 3-digit sequences and 5 2-letter sequences, then we would multiply, and we would find out there would be 7 times 5 different license plates. But those numbers were wrong. I just wanted to show you why we're multiplying. How many 3-digit numbers are there? Well, there's one way of doing it. You can look at them. Up to 99, well, those are 2-digit numbers at the end. Then you have 100, 101, 102, 103, all the way up to 997, 998, 999. Well, let's consider, just take away 99 from each of these numbers. Then the first one would be 1, and the second would be 2. You take away 99 from, why did I take away 99? Because I wanted the result to be 1 first. 100 minus 99 is 1. 102 minus 99 is 3. 103 will be 4. I meant to put 3 dots in here. If you take away 99 from here, you get 798, I think. How about 898? You take away 99 from here, you get 899. You take away 99 from here, you get 900. That is, this number, 100, was the first number. This number, 101, was the second number. 999 was the 900th number. And those are all the 3-digit numbers. The next number would be, after 999, would be 1000, of course, which is 4 digits. And anything before 100 will either be 2 digits or, at some point, 1-digit numbers. So you can count it that way. So it's 900. Or you can say 3 digits and then 2 letters. Well, 3 digits. To be a 3-digit number, well, you know what? Actually, I guess I made one mistake. When it comes to license plates, it doesn't, see, this 072, we did not include that as a 3-digit number. But the problem is that 072 can definitely be a plate number. So I guess I blew that one, sorry. I guess we can start from 000, 001, all the way up to 099. So let me do this a bit more carefully. can have 0, 0, 0, 0, 0, 1, 0, 0, 2. So actually this will be easier. Eventually to 998, 999. Well, forget the top one. How about we call this the first number, and this the second number, and this the third number, and that'll be the 999th number, and the top one will be the thousandth number. There's 1,000 different 3-digit numbers we can come up with. 3-digit sequence. If I say number, I won't include 0 at the beginning. Okay, but the easier way of doing this is saying, well, the first position can have one of 10 digits, and same with the second. The digits are 0, 1, 2, all the way up to 9. There are 10 of them. There are 10 of them, because 1 through 9 is 9, and then you add on the 0 digit, there was 10 of them. The third digit is any one of the 10. And you multiply, because first you pick a digit, and then you pick a digit, and then you pick a digit, and then you pick a letter, which is 1 out of 26, and then 1 out of 26 again. So if you multiply those 5 values, 10 times 10 times 10 times 26 times 26, you will figure out how many license plates there can be with 3 digits followed by 2 letters. When you go from state to state or county to county, get a feel of how their plates are in that county and figure out how many different license plates there can be. Okay, let's go on and do a different type of counting problem. Suppose there are 5 people. They all go into a meeting and they don't know one another, or they do know one another, and everyone's going to shake hands with everyone else. The question is, how many handshakes will happen? So there's 5 people, and they're all going to shake hands with one another. No one person is going to shake hands with themselves, and every person will shake hands with the other 4 people. So we'll call it people A, B, C, D, and E. And we'll put them in a circle. And we'll see. A shakes hands with B, A shakes hands with C, and D, and E. And B shakes hands with A, but I already have that. So B shakes with C, and B shakes with D, and B shakes with E, and that's done. C. Well, C already shook hands with A, and C already shook hands with B. She only shakes hands with D, and person E, well, needs to. She does not only shake hands with D and E. She already shook hands with A, B, and C. Now D. D shook hands with everyone except E. And E already shook hands with everyone. So basically it's 4, 3, 2, and 1, which is 10. There will be 10 handshakes. Okay, you can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That's a very special type of graph. So 10 people will shake hands with one another. Okay, this completes the section on counting. Do lots and lots of problems like these. Have the answers hopefully worked out for you, and then you could see how they come together. Initially they all look alike, but at some point there's only a handful of different types. I tried to cover most of them, and just study hard and you can do it. Thank you.